Hi, so again, my name is Avery Schmipf. I'm in the chemistry department. I'm a chemistry major, and I've been working in Dr. Rebecca Thompson's lab for the last 2 years, making self-assembled monolayers, and more recently looking at protein absorption on these self-assembled monolayers. And so I'm going to be speaking a little bit more about that today. So just to give you an overview, I know that you just sat through another presentation on SAMs, but they're self-assembled monolayers, and so what that means is when we introduce specific molecules to a specific substrate, as you can see from this image right here, here's the substrate that the head group is binding covalently to. Certain molecules will spontaneously assemble in a way that we would ideally think would be pretty well ordered, like this right here. And so some really important applications for this are like biosensing or immunosensing, and one of these can be like detecting different cancer biomarkers, using like electrochemical biosensing to look for other diseases or biomarkers, which has been really important, and then also like for molecular detection for other things, maybe not very biological. So some examples of that might be nitroaromatic compounds, looking at TNT. So one example of that is a group that made self-assembled monolayers for detecting nitroaromatic compounds swabbing in the airport. So like they would go through security and like randomly swab people. Well, it was an idea that was proposed, and they were able to use SAMs to detect these nitroaromatic compounds like TNT in very small quantities, which is really good. So things like that are some examples of how SAMs have been used previously, or how people propose they be used. So some of the different characterization techniques that I've been using in my research for the past couple of years have been infrared reflection-absorption spectroscopy, or what we call it IRIS. So this is a type of IR that lets us look at reflective surfaces specifically. And what we're working with is gold surfaces as our substrate. And so this has been really helpful since gold is reflective. And this lets us know more about the surface composition, letting us look at different vibrational modes for different types of bond stretching. And so it lets us know like which types of bonds or which types of dials are present on the surface. The next type of characterization method that we use is continuum gominometry. So what this entails is putting a water droplet onto a surface, and we take the angle of that droplet relative to the surface, and it tells us more about surface wettability in terms of like hydrophobicity or hydrophilicity of the surface. So it's been really important and a really like fast and significant way to like really get quick information from our samples versus where IRIS takes a long time to set up and can be pretty time consuming. And then finally we used polarization, modulation, infrared reflection absorption spectroscopy. So this is just a modified version of IRIS that takes away some of the things that we don't want to see at the surface of what's going on in our samples. So it might subtract out like water, like vapor that's in the air because of the humidity. But ideally we minimize that, and then also by using this modified type of infrared, it helps us to more selectively look at what's on the surface, and it's much more sensitive. Oh, and just to go over some types of organization defects in SAMs. This image on the right just shows some of the different like common types of organization defects. So one thing that we're really focused on, or what I've been focused on in this group has been, in my time doing research, is how does the order of self-assembled monolayer formation on the surface actually impact protein absorption. So these are just some of the different things that we might see, but our techniques don't let us look at this. So we have to infer and look at the literature for these types of things or expand to other instruments, but these are just some of the things we might see. And phase separation is one of the more common ones for mixed self-assembled monolayers, where we take two different types of molecules and try to self-assemble them, co-absorb them onto a surface. This is just going a little bit more into contact angle. So here, an image on the very left is showing what it maybe like a hydrophobic droplet would look like on a hydrophobic surface. And on the bottom left, this is an image that I took using our technical setup of what a hydrophobic surface might look like. And then the hydrophilic one has a very low contact angle, usually under 90 degrees, which is seen on the image in the bottom right here. So how I said before, like our SAMs are made up out of, in the previous images shown, made up as made up of, right here, the substrate, this head group that binds covalently to the substrate gold. We have this alkyl tail, and then this functional group that we can change out using different molecules. You can see these are the different ones that we use. So silver is well known for having really strong bond to gold, so we use thiols. And the three ones that I've been looking at specifically in my research are these three. One that's a hydroxyl terminated thiol, which we would call MUD, a carboxylate terminated thiol, which we call MUA, and a methyl terminated thiol, which we call DDT. And so, like I said again, like these ones are definitely more hydrophilic thiols, have hydrophilic properties. This CH3 methyl terminated will have more hydrophobic properties, which we see in contact angle. So now, like moving on to now that I kind of explored the characterization methods and kind of what our lab does, I really spent a lot of time working on characterization with these methods for our samples. So over the past summer, I found this article by one group who performed a study where they had the same materials as we did, the same instrumentation as we did. And this was our first attempt at making mixed subsummer monolayers of two different thiols. And so this is their data from this experiment, and it just shows contact angle decreasing as they decrease the hydrophobic character or decrease the amount of methyl terminated thiol in their SAMs. And so they're making different ratios of mixed SAMs. And then they monitor that in infrared as well in iris by monitoring this peak on the very left. And so this peak is specific to DDTs, only seen DDT, and this is the CH3 stretching stretching region of the molecules that we're looking at. So this is the CH3 asymmetric stretching region. And as that peak goes down, is the number or the quantity of CH3 or DDT goes down. And so just to kind of give you more of a visual representation of what these mixed SAMs look like. So on the very left, we have what we would think or what we would see ideally like as the DDT SAM, where we have just methyls. And then on the middle, we have an MUD SAM where we have just the hydroxyls, the OH. And then here's an example of what a mixed one might look like. In theory, we have varying groups of the methyl and the hydroxyl. So now these are the results that I had from my iris data, from my infrared data, repeating from this other group's experiment. And so what I did was I made the same ratios of mixed subsummer monolayers and also made a DDT and an MUD subsummer monolayer and monitored that same exact peak at 2,965 wave numbers and saw that it was decreasing just like it was as reported in the literature. And so this really was some of the first steps of ensuring we can make these mixed subsummer monolayers, we can make these mixed SAMs, and we can accurately characterize them using our instrumentation that we have in the lab. And so then moving on to the contact angle goniometry, what I did find was pretty interesting. So for this blue trend line, we saw that matched up with what the literature showed in that it's pretty linear, and that as you increase the MUD character, the contact angle goes down, which makes sense. Contact angle going down, more hydrophilic, and that would make sense if we have more of the hydrophilic MUD. But for this pink trend right here, you can see that the lowest the contact angle really goes is around 40 degrees. It doesn't go any lower than that, which is not as what is shown or what's reported in the literature. And so we have some theories of this, and one of the things that we think is happening is that maybe there's a double layering effect where excess MUA molecules in solution are via hydrogen bonds binding to the SAM in solution and creating kind of a double layering. So instead of it being an MUD where it looks, or excuse me, MUA where it looks like for our terminal group, we see the water for the contact angle is sticking in the thiol, sticking up instead. And so this is something we want to kind of explore more with maybe some pH experiments, because that MUA can be deprotonated. So just playing around with that, trying to see how that works. But in this situation, the MUA is protonated, which leads to that hydrogen bonding. So since I was able to like successfully characterize those mixed up with some of the monolayers, I wanted to move on to looking at BSA absorption or bovine serum albumin absorption on these different SAMs. So BSA is the most abundant blood protein in the body, and it has lots of anticoagulation properties, and it's really important for, like Vanna talked about, for medical implant devices and things of that nature. And we wanted to choose one that was really well known in the literature, and so this is why we chose this protein. And so what I decided to do was look at high concentration and a low concentration of BSA solutions and put that onto different mixed DDT and MUT SAMs. And so the black spectrum is a low concentration for 30 minutes, and then the red spectrum is a high concentration for 10 minutes. And what this shows is for the MI2 and the MI1 over here, these right two peaks, it does look like the red is absorbing more at the high concentration, but then it looks around the same or maybe reversed for this other situation for the MI2 prime. Now looking at same concentrations and same time in solution for other types of SAMs, we look at MUD, DDT, and then the mixed MUD and DDT. And so what we see here in the right two MI peaks is that it shows us that the MUD has the highest absorbance at MI2 and MI1, and then they're about the same, and then a little bit less for DDT at this MI2 prime. So kind of like what we can gather from this is it's too difficult to really tell from, aside from the evidence that we get that MUD might be absorbing more of the bovine serum albumin at low concentrations. It's a little bit difficult to tell, and we think that we'd like to move forward and try higher concentrations or varying concentrations for one type of SAM. And I think this might be the best idea moving forward. So these regions are also going to be well known to be used for learning more about BSA conformation. So what we want to do is, like, from here moving forward, this is my most recent data that I've edited and collected. The most recent thing that I want to do moving forward, well, I'm going to be here very much longer, but do varying concentrations increasing for one type of SAM instead of trying to look at different types of SAMs and then being confused. But I think this is really good information, kind of agreeing with what Anna said before, where she was seeing that MUD was absorbing the most BSA. But we definitely like to repeat these experiments, but yeah, so moving forward, we want to just again look more into how concentration is impacting on BSA on SAMs, and looking at that with PM iris as well as iris. And so for that, like, we would like to just look at, instead of varying types of SAMs, maybe look at pick one SAM and then gradually increase and see how those peaks are affected. Sometimes in the literature they've reported that not all peaks increase proportionally as concentration or as quantity of BSA is increased. And so that's something to consider as well, since we're trying to quantify amount of BSA using this peak information. And so next we would like to try and look at PM iris, try to put PM iris data in aqueous conditions. So one of the great things about this modified iris or modified infrared is that it lets us look more selectively at the surface, removing out a lot of things that we don't want. And so one of those cases could be water. So we would like to create like a chamber and do like an in real time collection of data as we're inserting BSA solution into like a chamber with our samples. And so that's something that we think would be really interesting to see how that works. And then finally, we would like to see which one of those peaks, which one of those anti-peaks in the BSA would be the best for probably looking at and quantifying BSA absorption, because some of them are known not to increase proportionally to quantity of BSA, and some of them aren't. And so looking more further into that and seeing, because not all of them are equal in terms of that increase or decrease in BSA absorption, we'd like to just find out which one would best do that through experiments and through the literature. Are there any questions? No.
And what do you think will happen if you were to repeat this experiment?
I would think it probably should the same thing in terms of what it looks like for the MUA. I guess it would also have to be like thinking about if it's, I mean, it would still be hydrophilic, it would still have those lone pair electrons to be drawing those positive charge residues off the BSA. If that were the case, if that's how it's interacting with the BSA. So I would expect it, if this is the case, if we are seeing the MUD is absorbing more on the, or seeing if BSA is absorbing more on the MUD, that would maybe be the same case for MUA, that carboxylate group. I don't really know how they would compare to each other. Yes?
So is there a way to essentially wash the BSA off, and so then you can collect it and use like some sort of protein analysis? So as opposed to measuring while it's stuck on there, you measure how much
Right.
once you take it off.
What we do like in our preparation process is like, because it's like soaked in like a BSA solution, we do rinse off like whatever excess is already on there. So the only like reason I could think of like in terms of like getting the BSA absorbed under the surface off would be some type of like chemically removing that, and that might, I guess maybe denature or maybe disrupt the protein. And so I'm not really sure about that, but how to go about that.
Even if you like nature the protein, so like the brand assay to
Mhm.
measure Albumin analysis.
Yeah, I guess I have to think more about like how to go about doing that. But yeah, that's a good point.
Any other questions? Alright, so you can go ahead and thank you for your
Yes, now I know it's expected. I've got it. Oh, all right. So Avery is also one of the very first students to join my lab. He actually joined my lab in the summer of 2020 before I got here to do a virtual internship. And if that is a dedication to research, I don't know what is. So Avery has also been instrumental in getting a lot of our research off the ground. Like Dan with the GCM, Avery is the one who figured out how to use that contact angle instrument, developed what the protocols for it, and did a lot of those preliminary experiments and let us figure out what we're even seeing in our lab. So without Avery, we would be in a very different place. And I'm really excited to just now just a cool job that continues her love of research and kind of exploring surface phenomena in some way. So